A question here about refraction. So wavefront diagrams are used to explain why light refracts when it passes from air into glass. So refraction is a change in direction, and that happens due to a change in speed of the wave. So it's this one through the middle that's showing you the direction of the light ray. So the light is travelling through here and you can see there's a bend in it. So it's changed direction as it's entered the glass because it's slowed down. And you can see it's slowed down. Each wavefront isn't travelling quite as far. They're closer together. You've got a shorter wavelength. So these lines here that are at right angles to the ray are called wavefronts. Okay, so we can explain this effect by talking about those wavefronts. So this light travels along, and when it enters the glass, it slows down. That's your first point. Okay, and what we can see here is that part of the wavefront enters the glass and slows down before the rest of it. Okay, so the speed of light in glass is less, 1 mark. The edge of the wavefront that enters the glass slows down, 2nd mark, while the rest of the wavefront that's still in air carries on travelling at the same speed. That's what causes your change in direction. Then we've got a ray of red light entering a glass prism. Complete the ray diagram to show the ray emerging from the glass prism. So what the rule we have is when something goes into something more dense, such as glass, it bends towards the normal. So you can see before it enters the prism, you've got quite a big angle between the normal line and the incident ray. That's the one going towards. When it comes through here, it's going to bend so that the ray travelling through the prism has quite a small angle with the normal. So it's going to go sort of almost straight across. Okay, that will be 1 mark. Your 2nd mark then is for drawing on another normal at right angles to this boundary at the point where your ray that you've drawn hits this boundary. Okay, the point where it emerges, you've got to draw a normal at right angles. Okay, and this time your ray has to bend away from the normal. Okay, so again you'll have quite a small angle, and this one is going to bend away from the normal after it's emerged. And you can look at diagrams of that on the internet to double check what it looks like. So white light is made up of a continuous spectrum of different wavelengths that all travel at 3 × 10 to the 8 meters per second in air. So 300 million meters a second, that's the speed of all electromagnetic waves in air. Rainbows are produced because different wavelengths of light travel at different speeds in water. Figure 3 shows the speed of different wavelengths of light in water. So, explain why violet light is refracted the most as it enters the water. So here you just need to know that violet has the shortest wavelength. The way I like to remember that is remembering that the gamma ray, X-ray, ultraviolet side of the electromagnetic spectrum is the shorter wavelength end. Violet, ultraviolet, both short wavelengths. Red, infrared, both on the long wavelength side. So violet light is over here, is going to be the 400 nanometer. If you just say violet has the shortest wavelength, that's fine. And if we read off, we can see shorter wavelengths, slower speeds. So when it enters the water, violet light is going to be travelling slower than red light, which will be over here. And we know that they're both travelling at the same speed before they enter the water. So red and violet both travel at the same speed in air, but when the violet light enters the water and the red light enters, the violet light will be travelling slower. This means the violet light has had the biggest change in speed, therefore the biggest change in direction, because refraction is caused by a change in speed.